data structures in algorithms. Yeah, so we consider another important topic here, data structure. All right. So C.1, search unordered arrays. That's a simple problem, simple computing problem. But we can look at the importance of the data structure role. All right, our problem number 2, search an unordered array. Given an unordered array, here we use this representation with indices from 0 through n-1. Here you can see there are n elements in this array, n elements. And if we use the problem size concept, problem size in this array, number of elements, that's n size. All right, and a search key k. Given, the question, find an index I such that k equals a of I. That's the search problem. Simple search problem. It's very easy. Everyone can solve it quickly. I believe you can already find a solution quickly. But here, I like to do some discussion. So we try to learn some basic concepts in this simple example. All right. The problem type here, there are some basic problem types in this class. And this one corresponds to one of the basic problem types. That's the search problem. Search problem, all right? And the data structure is array here. All right, And the reference for this material, section 2.1. All right, here, we want to look at this question. Why the data structures are important in algorithm design. Here, we use probably the simplest data structure, array. Later, we will learn some advanced data structures. So at the beginning, so let us just look at the simple data structures. All right. Here, the reason, what's the reason to use some special data structures? So here, the typical reason is this. Through data structures, we can make our data well organized. Usually, the data is given in random order. No specific order. If when you work on the given data, if the data is not organized, you may need to spend more time to do the processing. But if you can organize your data in some way, in some special way, then you can improve the overall performance. So that's some, common practice people use. All right. So here we want to take advantage of the structure for better performance. To understand this point, we need to use many examples later. All right. So here, so for this simple example, first we already have a solution. You just compare element one by one with the given key until you go through all the elements in this array. right? That's the solution. Yeah. All right. So here we just do some analysis. Yeah. All right. The basic operation we use here, comparison. You do not need to do addition, multiplication. You only need to do comparison. Okay, yeah. So what kind of comparison? Compare K with the current element in the array, A of I. Yeah. When you start, you set initial index value, I equals 0. Yeah. Then you do iterations. If K equals A of I, you can return the value of I. When K not equal to A of I, you need to do more comparisons. Yeah, all right. So that's the, solution. Yeah. So here, iteration, you need to do further iterations. Yeah. Do another round comparison. Okay, and so on until you reach the end. Yeah, the end, this is the end point. Yeah, if after you do the comparison with the last element, still you cannot get a hit. Yeah, no element equals the given key K, you just return -1 for your function. Okay, yeah. So that's the whole solution. Yeah. But here we want to do discussion on the efficiency analysis. Yeah. Our main focus here is for efficiency analysis. Yeah. Okay. Yeah. Yeah. Here, the algorithms, there is a name for it. We call it sequential search. You apply comparison sequentially, sequential search, or linear search. Yeah. Linear search, so that focus is on, efficiency. Now, efficiency is a linear function. Okay, yeah. So that's the linear search. Yeah. Sequential search, so we do comparisons in a sequential way. Yeah. All right. Now, efficiency analysis, a little bit. Yeah. To do here, let us count the number of comparisons for the stable measure for the efficiency. Okay, yeah, yeah. So let us do the chart here. Yeah. Let us consider all the possible cases for the comparisons. Yeah. All right. Here, look at the given key. Key equals one of the elements in the given array, and the last case, no match. Now, so we consider those n+1 cases. The total, there are n+1 cases. Okay, yeah. For each case, let us look at the number of operations. Yeah, all right. If K equals the first element, we just need one comparison. That's it. Okay, yeah. So we return the result by one comparison. Okay, yeah. That's the smallest comparison number. Yeah. If K equals A of 1, 2 comparisons, and so on. Okay, yeah. Until the last element, K equals the last one, n comparisons. Then no match. If no match, you need to compare all the elements. For the no match case, that's also n comparisons. Okay, yeah. After that, now we can do, we can do some summary. Okay, yeah. Let's look at all the cases for some discussion here. Okay, yeah. First, we notice that Case 1, that is the best case because the number is the smallest, the best for us. Okay, yeah. Just the one comparison, we can find a solution. That's the best we can have. So we call it the best case. Okay, yeah. Then the last two cases, that comparison number equals n, the worst case. Okay, yeah. So that's the worst. Yeah. So the best case and the worst case. Yeah. That's very straightforward. Yeah. But there is another important view. Yeah. We want to see what is the overall efficiency. We want to measure the overall efficiency. Yeah. Definitely, best case, it's not a good way to evaluate, to measure the overall efficiency, right? The best case, you cannot use best case 1 for the overall efficiency. Worst case, not good number, you cannot use the worst case number n to measure the overall efficiency, right? Yeah. So here you need to use a new way for overall efficiency. That's the average case. That's the concept. We need to, put a lot of emphasis here. The average case efficiency, that concept. Now, I want to do some discussion here. The measure should include all the cases. The best case, you only use one of the cases. Worst case, you also use one of the cases. But here you need to consider all the cases, not just one case. Yeah. So that should be the average case efficiency. Yeah. Yeah. But if we want to consider all the cases for this particular question, we need to make some assumption. Yeah. Otherwise, the answer could vary, quite different. Yeah. So we need to make a little more assumption to provide better description of the answer. Yeah. So let's see. So what is the assumption we need to make?